Rational functions. So what we're going to concentrate on today is some of the definitions surrounding rational functions, how to graph them, how to find some points that help us do that. But the do now you should do obviously right now. Pause the video, try and do the do now. This should be a review from the last section we did. And then come back. So pause now, and then I'll find the actual answers that I put in here. So this is what I'm getting with the asymptotes. I started with the parent function was number 1, and then use that parent function to develop all the other ones with the mappings to help me find some coordinates, the asymptotes, and some coordinates to help me graph them. We need to define the rational function. I pre-filled this, so I'm just going to erase here. A definition of a rational function is any function that can be written as the quotient of two polynomial functions, n of x and d of x. I used n for numerator and d for denominator, in the form f of x is equal to n of x over d of x, where d of x cannot equal 0. So you don't have a 0 in the denominator. I should say we account, I can't spell, sorry, account for this. Let's try that again. Account for this. There's different ways to do that. Either we could have holes or vertical asymptotes. But for me to explain what vertical asymptotes are, we need to define asymptotes first. So the first thing I want you to do is look it up. Look up the definition for an asymptote. Copy and paste it. You could put it right in the middle of the page or on the side. I put it on the side because it shifted my pages around weirdly. So I went online and found the definition down here at the bottom. What I want you to concentrate on is this: the analytical geometry, an asymptote of a curve of a line. An asymptote of a curve is a line such that the distance between the curve and the line approaches 0 as one or both of the x or y coordinates tend to infinity. Now, projective geometry we don't need to worry about, but I just highlighted that little piece there. Another definition I found: a line that continually approaches a given curve but does not meet it. This one, you have to be careful because it can do. It starts behaving like. So the wording for that is not my favorite, but we'll discuss that as we go along. Meet it at any infinite or at any finite distance. So that one is a little, I'm not super happy about, because the function can meet an asymptote or intersect an asymptote. It just doesn't stay there. Let's put it that way. So I want to put in like an informal definition for us. Okay, so here, informally, it's a line. It can also be a curve, so it doesn't necessarily have to be linear, that the graph starts behaving more like as the graph gets closer and closer to the line, to the asymptote. And for vertical asymptotes, they occur where the graph is not defined. So provided there's no hole. We'll get into what a hole means in a minute. But first, vertical asymptotes, in other words, in practical terms, is we're going to look at where the denominator is 0, provided the numerator is not 0 at the same time. So here, set the denominator equal to 0. Then, that should be an n in there. Then solve for x. As the graph approaches the asymptote at x is equal to a, from the left or the right, the graph approaches positive or negative infinity. So what that looks like, and here again, I have to put a little caveat on that. Provided the numerator is not 0 for x is equal to a. Because if that happens, then there is actually a hole there, and we have to take care of that first. But let's look at it graphically. So what that means is, and I used limit notation here, and the way to indicate limit notation is that as x approaches an a value, some value, the function itself is going to infinity. Graphically, what that means is that you see this little negative right there? at the top of A to the top right of A, that means I'm approaching from the left side, so from the negative side. And because it's going to infinity, we're going to approach the asymptote and start traveling along. So it's going to start behaving like, so it can't actually cross that vertical asymptote because the function is not defined at x is equal to a. The other one, or it could also be I'm approaching a from the left-hand side, but instead the function is going to tend to the negative infinity. That means it's going to start going downwards here at that asymptote. That's a vertical asymptote, okay? Either it's going to go to positive infinity or negative infinity if I'm approaching from the left, or it could do it from the right, or it could do it from both sides. So in this case, that means to show that we're approaching from the right instead, so that's from the positive end of the number line, and going to positive infinity, it would look like this. Vertical, as x approaches a, as we get closer and closer to a from the positive side of the number line, it's going to go toward positive infinity. Or it could approach from the positive side, so from the right side, and approach negative infinity. Those are the options for vertical asymptotes. And the way we find the vertical asymptotes is take the denominator of the rational function that's said equal to 0. Whoops.